Welcome to the electronics class for November the 3rd, Election Day. If any of you are 18 years old, I hope that if you've not already voted, that you will before the day is over. A really important thing to do. Okay, so I can't really think of any administrative details we need to talk about. Let's just jump right into last time's quiz. Most of you did quite well on the quiz. Let's uh, let's go in and talk about the problems that were on there. So intro to transistors was what we did. So if I click on that one and wait a little while, okay, let's do a preview so that way it'll look more like what you guys actually see. Okay, so first question is what kind of transistor this is. Okay, now we only talked about one type of transistor, and this is the type that we did talk about. It was a bipolar junction transistor. It's the NPN variety. Uh, let's take a minute and talk about the other kind. So remember that the transistor is kind of like you take two diodes back to back. Okay, and with a diode, this is the symbol for a diode right here. Okay, and so diodes are made of what we call a p-n junction, and it always flows from the positive to the negative. So this is the p side, this is the n side of a diode. So that means that this center part where they're connected back to back, that would be the p part. And so this would be the n part of that diode, and this would be the n part of that diode. So now if you look at the transistor, then if you were to go through it this way, you'd hit N first and then P and then N. So that would be an NPN diode. And this arrow right here is meant to represent that diode. Now, there are other ways that we could do diodes. So what you can do is you could take the diodes and you could put them together like this. Okay, so that the two diodes are both pointed in. Okay, so again, with a diode, this side is always the P and this side is the N. And so what we've got here, if we follow through there, it would go P and then N and then P. So an NPN transistor is the most common type of bipolar transistor. Now, there are other kinds called MOSFETs that we are going to talk about probably next time we meet, but not today. They're a different variety completely, similar in many regards, but very different in others. Okay, so of the bipolar junction type transistors, there's PNPs and NPNs. NPN is the most common bipolar junction transistor, but there are times when people use PNPs. And with a PNP, it runs a little different. With an NPN transistor, the kind that we've been using, if you want it to turn on, what you need to put positive voltage here, and you put this one to a lower voltage or ground. Okay, and then that allows the current to flow, and so that turns it on. And so then if you've got a positive voltage here, it allows it to go. If you were to do the other type of transistor, which is called the PNP, okay, this is the diode that turns it on. And in order for it to turn on, you need the current to flow this way, and it's only going to flow this way if this way is grounded. Okay, so this is going to be your positive voltage. So what you want to do if you've got a PNP transistor is you want to take the base and you want to put it to ground, or at least some voltage that is less than the voltage up here. Doesn't have to be ground, but it does have to be less voltage than you have up here. Whereas with a PNP, or I'm sorry, with an NPN, okay, you want the base to be a higher voltage than you want the emitter. The emitter doesn't have to be a ground, but it does have to be at a lower voltage than your base is. Okay, so PNPs and NPNs, when you take the test, by the way, we haven't talked about this. Let's take a minute and talk about it. there is a state mandated standardized test that you guys are going to be taking in January. I don't write the test, the people of the state of Utah write it. And you will be taking that test. And so they will be asking you to identify transistors. So you need to know from looking at the symbol, you need to know which one's a PNP and which one's an NPN, and also which ones are MOSFETs, which is something we'll talk about very soon, but not today. Okay. So make sure you understand this one. Sorry. Okay. So this one here is NPN, and then the other kind has the arrow like that. Okay. And so this is what you look at. So this tells you that this is the PN junction right there. So that way you know that the base is the P. And so here you look at this. So this tells you this is the PN right there. So that tells you the base is the N. So you know then that this is a PNP, whereas the other one over here is an NPN. Okay, so just make sure you know that. Okie doke. Question number 2. Okay, what are 3 common applications of transistors? Well, we talked about some of them. Okay. Temperature, definitely not. Amplifier, yes. And in fact, we did some examples there. We saw it used as an example. We used as an amplifier. Logic gate is one thing that I mentioned very briefly, but only briefly. That is what we're going to focus on today, in fact. Today, we're going to learn what a logic gate is and how a transistor is used as a key component of a logic gate. Giving off light, nope, that's not a transistor. Soothing out voltage spikes, nope, that's a capacitor, which is something we haven't talked about yet, but we will. Using a low voltage signal to turn a larger voltage on and off, yeah, that's where, remember how we used the transistor to turn on that motor? And it was a 12-volt motor, but we were able to turn it on using the Arduino. Okay, that so we're using the transistor in that case as a electrically controllable switch, which is also called a relay sometimes. Okay, matching the name of the transistor with the operating mode. So saturation mode, okay, that's when the current is fully flowing. The transistor is on as much as it possibly can be. So it's going to act like a short circuit. So it means that the current is flowing freely from the collector to the emitter. That's when the thing's in what we call saturation mode. Cutoff mode is when the thing is turned off. Okay, so the transistor is in the off position, it's like a switch in the off position. And then active mode, that's when you're using the transistor as an amplifier, where the current is, the output current is proportional to the current that's flowing into the base. It's that's what you did an activity on. Okay. All right. So speaking of activities, okay. So this was the activity that we did. Now I did have a couple students email me saying that they were having a little trouble with the activity. So let's talk about it right now. Okay. So you should have built something that looked like this. You should have a transistor, which you have got hooked up so that we've got a power supply here, and we got some voltage that comes into the base. So that's the base of the transistor, right? And we've got a resistor here. So the resistor limits it so that we only have a slow trickle of current coming into the base. But that's all we need is a slow trickle. And then if you can get a slow trickle coming into the base, so then it goes back into here, that's enough to turn on the transistor. So that allows a large amount of current to flow through the transistor. Okay, so a large amount of current is controlled by a small trickle coming into the base. That's the way that it works. Okay, so the first thing was to make sure that you hooked it up properly this way. Okay, so now if we start the simulation going, well, let's start it off down here. Let's start off with 0. So that means that if our voltage here is 0, then obviously our output is 0. So we have nothing going into the base. That means nothing can flow through here. So the transistor is off. Okay, so they call it cutoff mode, or think of it as a switch in the off position. So even though we have 10 volts trying to push the current through here, the transistor will not let it go because it's in the off position. Okay, so let's turn on the voltage a little bit here. We don't need much, just a little trickle is all we need. Okay, all right, let's make it even smaller. Let's make it let's make it really small. Let's take that voltage down to, let's try 1 volt. Okay, that's good. I like it at 1 volt. Okay, did you notice that by clicking on here, I get to type in the numbers, and so that hopefully you guys remember that allows you to change the voltage in little tiny small steps, smaller than you would be able to by clicking up here. Okay. So now some people ran into problems when they were calculating the gain of the transistor because they weren't used to dealing with microamps. Milliamps is something we've dealt with before. We know that milliamps is 10 to the negative 3 amps, or in other words, it's 1/1000th of an amp. This guy right here is one that maybe you haven't worked with very much before. And so I saw people had trouble with it. This is called a microamp. And so that's 10 to the negative 6 amps, which is the same thing as 1/1,000,000. Okay. All right. So then when you put into the numbers into the calculator, what you want to do is you want to put in the output current divided by the input current. So you want 75.4 times 10 to the negative 3 divided by 257 times 10 to the negative 6. Now, when you put this into your calculator, you have to be very careful, because if you type in 75.4 times 10 to the negative 3 divided by 257 times 10 to the, hang on a sec while I fix that. Okay. 10 to the, and I still can't get it right. Okay, one of these times I'm going to get it. This time, this will be the time. To the negative 6. If you type this into your calculator, you will get the wrong answer. Okay, because calculators work on, remember PEMDAS, please excuse my dear Aunt Sally. Okay, so the calculator does exponents first and then multiplication, division second. Okay, so the calculator is going to do this and this, and then it's going to do the division and multiplication and division, and so it's going to take, it's going to do it wrong because it's going to take these numbers and it's going to divide it by this number, and then at the very end it's going to take all of what it got here and it's going to multiply it by this number, which is not what you want. So it's very important that you have to put parentheses in here. Okay? So if you want to do this right, it's essential. Why do I have so much trouble putting that symbol there? Okay. You have got to put a parenthesis here and here, and you got to put another parenthesis here and here. Otherwise, you will get the wrong answer. Okay, so when you do this right, you should get 293. So let me make sure. So 75.4 times 10 to the negative 3 divided by, with parentheses, 257 times 10 to the negative 6. And yes, 293 is what we get. Okay, so the gain of this transistor then, with these settings that you see right here, okay, using these numbers, I get that the gain, which is called beta, is 293. What if I had chosen a different setting for my guy here? What if I had gone up higher to a setting like this? Okay, so now I've got a whole different set of numbers. So what I'm going to do is I'm going to do 1.46. Notice that's amps now, not milliamps, so I don't need times 10 to anything. Divided by 4.98, and that's milli. So that's times 10 to the negative 3. Okay, so let's do this. So 1.46 divided by, and then with parentheses, 4.98 times 10 to the negative 3. And what do you know? I get the exact same number. I get 293. So what you're going to find is you can change this number to anything you want. This number here will always be 293 times whatever your input number was. Okay. Now, I do need to warn you that if you were to do this with real transistors, you will find that they vary from one to another, even if they are transistors that you bought at the same time from the same batch. Let's say that you buy a dozen transistors. And so you get a little bag, 12 transistors in, all made at the same time by the same company. Okay. If you were to measure the beta for those transistors, you'll find out that each one is going to be slightly different, because the process of making transistors, it's very tricky. It's pretty much impossible to get all transistors exactly the same. Okay, but they'll be close to each other, but don't expect them to be exactly the same. Okay, so that's pretty much it for the quiz last time. Anybody have any questions about the quiz that I haven't covered? Not seeing any, not hearing any. Okay. All right, let's see. Let's go in here. So just a quick reminder on how things work here. Okay, so I've already pretty much talked about this when we were going over the quiz. So just remember that a transistor is made of two back-to-back diodes, at least a bipolar junction transistor is. So let me just stop for a second here. Okay, what you're seeing here is true of something that's called a bipolar junction transistor. Okay, also sometimes called BJT. Okay, so there are different types of transistors that are made by a very different process. I'm not going to talk about them today, but I am going to talk about them later, maybe next time we meet, maybe next week. We'll kind of see how things go. Okay, this is only one type of possible transistor. Okay, and difference between an NPN and a PNP, I think we've already talked about that. So I'm going to skip over that if you don't mind. Okay, so this was the example where we used the transistor in order to turn on and off a motor. So the motor that you see up in the corner here, this was a motor that requires 12 volts in order to run, and the Arduino can't do that. The Arduino can only put out 5 volts. And to be honest, it's not even that. Because if you got a real Arduino and you turned on the pins and you measured the pins, you'll find out that it's actually somewhere between 4.5 and 5. It's somewhere in that range there. And it's usually not 5 volts, but it's usually at least 4.5. Okay. And so that is clearly not enough voltage to run this motor. And also this motor takes more current than an Arduino can put out. The current, the maximum safe current to have an Arduino put out is about 20 milliamps. Okay, and this motor takes a lot more than 20 milliamps. So if we try to run this motor directly from an Arduino, we will destroy the Arduino. So what we do is we get a power supply, or we get a 12-volt battery. That works too. Okay, but so we get a 12-volt power supply or a 12-volt battery, and we use the resistor here. I'm sorry, we use the transistor here as a switch. And sometimes you'll hear it referred to as a relay, because a relay is basically that. A relay is a switch where a very weak input signal is allowed to control a very strong output signal. Okay, so what you're seeing here is one very common use of a transistor. And now I do need to be completely honest here. I am glossing over one fact that if you know a lot about transistors, you might say, hey, wait a minute, Mr. Hendricks, you're leaving out something very important. Transistors also have a maximum current that is allowed, okay? And it varies from transistor to transistor. Some transistors, the most you're allowed is maybe 500 milliamps. Okay, if you try to exceed that, you're going to burn out the transistor. Other transistors can maybe handle 1 amp. There are a few transistors that can go up to maybe 2 amps, but you don't really want to go much above that. If you need to go above that, then what you need to do are some special tricks, like take multiple transistors and hook them up in parallel. Okay, a bipolar junction NPN transistor can definitely not handle currents that are up above that. Even 500 milliamps is a little bit iffy. What you need to do is you need to look on the data sheet. When you buy a transistor, it'll have a number that you can look up on Google, and it'll tell you what is the maximum current. So the maximum current for this transistor is definitely greater than the maximum current on the Arduino, but it might not be enough to run a full 12-volt motor. So be careful about that. Okay, another application that we talked about last time was using the Arduino, or using the transistor as an amplifier. And so we just spent a few minutes talking about that already. So the idea is that you can have a very weak input signal, and what you get is you get an amplified output signal. And so this is very, very useful if you, let's say you've got a microphone where somebody's talking into the mic and you want to amplify it so that the entire crowd can hear it. This is the basis of an amplifier. This is how amplifiers work, is they have transistors in them to do that. They probably have more than just one transistor. Also, if you're looking at radio signals from outer space, you're going to need to amplify things. But here's an interesting point. Some of the radio signals that you get from outer space are really, really, really weak. So really, really weak. And so what you're going to find is if you have a super, super weak signal, even this technique that we use up here, that isn't really going to boost that weak signal enough. So what you need is you need a super amplifier, not just a regular boring everyday amplifier. You need a super amplifier. Well, this is how you do it. So some guy named Darlington, actually it might have been some lady named Darlington. I shouldn't be sexist there. Some person whose last name was Darlington. They got a great idea, amazingly simple and yet amazingly powerful. They said, take one resistor and use it as an amplifier like we've talked about, so that the output signal here is going to be amplified. Now, if you were to use the transistors that we have on Tinkercad, this output signal would be 293 times greater than your input signal, which is pretty darn good. But if that's not enough, easy way to solve that is take the output from the first transistor and use that as the input to a second transistor. Now, if this second transistor has the same beta as before, if it also has a beta value of 293, then the output signal here will be 293 times what that was. And so what you have is 293 times 293. So 293 times 293. So if you look at this as a pair, which is, by the way, it's called a Darlington pair, the beta on a Darlington pair is 85,000. So you can get some amazing increases there, okay? And so one thing that I kind of toyed with was maybe have you guys take some time and make this. But then I got thinking, okay, maybe it's not really the best use of our limited time. So I have done it for you. So let's go on to here. Okay. And so here's the transistor being used as an amplifier. Let's go back into my main collection here of nifty circuits. Sometimes Tinkercad is kind of slow at doing this. Tinkercad's a great thing, but it'd be nice if it was a little bit faster. Okay, so here we have a Darlington transistor amplifier. Okay, so let's tinker that baby. Come on. Now, I encourage you to do this. If you guys are bored, you're sitting around looking for something fun to do, I think this is a fun thing to do. Okay, so hopefully now you can see that I've got two resistors. So the output from my first transistor is the input to my second transistor. So I've got a Darlington pair. All right, let's start the simulation. Now, first off, let me take this resistor here. You'll notice I've got the resistor set for 100 kilo ohms. There's a reason why I did that. But let's start off. Let's just have it be 100. Let's just have it be 1 kilo ohm. That's how much the resistor was on our regular old amplifier. So let's see what happens if I use that here. So let's start the simulation, and what you can see is that my current is already maxed out. 5 amps is the most that my amplifier here the most of my power supply can possibly deliver. So I'm already I've maxed out. So what I need to do is I need to take this voltage, and let's take the voltage. Let's start off at 0 and let's see what happens. Okay, 0, so 0 volts, and I get 0 output. Okay, so let's take it to 0.2, nothing happens. And hopefully you guys understand why nothing happens is because these bipolar junction transistors are basically back-to-back diodes. And a diode has what we call a threshold voltage. And if you don't exceed that threshold voltage, nothing's going to happen. So 0.2 is less than the threshold voltage. 0.4, we're still less than the threshold voltage. 0.6, we're still not at the threshold voltage. 0.8, oh my goodness, still not quite at the threshold voltage in this case. So let's take it to 1 volt. And we should have reached it by now. That's 0.1. Oh, sorry. Okay, 1 volt. Okay, now we're starting to see a little bit out on our second power supply, just because we're round off error. So let's try 1.2. Okay, so now we're starting to get some stuff. Okay, but now some of you are saying, wait a minute, we're way above the threshold voltages that we measured before. What's going on? Why are we not seeing anything meaningful? Well, it's because we've got two transistors hooked up together now. So we have to overcome the threshold voltage from both of them. So it gets a little more complicated here, but we're getting close. I think if we go a little bit higher, okay, we should be able to get it. Bingo. Okay, now we are now running. We're cooking with gas. Okay, so we had to go to 1.6 volts in order to get anything to happen. But now that we're at 1.6 volts, now you can see that we are getting an output current of 4.4 for an input current of 51.3 microamps. That's not milli, that's micro. So the beta value for this Darlington pair, the two of them together, is 4.44 divided by 51.3 times 10 to the negative 6, because this is micro, which is 10 to the negative 6. Okay, let's put that in our calculator and see what happens. So 4.44 divided by 51.3 times 10 to the negative 6. And so I get 86,549, which is pretty much what we got before. We said that, but what we've said before was 293 times 293 was about 85,000. Actually, it was 85,849 is what it was. Okay. So you can see we are in fact getting the beta values we predicted, way more amplification than we had before. Okay, so now here, I think this is really interesting to play with. So remember, if we go down to 1.4, you can see that I've got nothing happening here. You can see I am getting something out here just because I am getting a trickle through, but nothing measurable on my input current. Okay, so 1.4 is not enough to make anything happen. So what I have to do is I have to go to 1.6. Now I get something interesting happening. If I go up just one step more, you can see I've already maxed out my my power supply over here. It can't do more than 5 amps. So I'm already maxed out. So there is only one voltage where I can get any kind of reading, 1.6. So if I go anything less than that, nothing. If I go anything more than that, I'm maxed out. So now you can see the reason why it is that I changed this resistor here. Let me stop the simulation. So this is why I changed that resistor. Instead of having a 1 kilo ohm, I make it 100 kilo ohms. Okay, so that makes it now so that I have a whole lot more range to play with. So I can, now I'm still maxed out. It didn't take me very much to max it out, but I can still, I have a much wider range here to play with. So if I start here at 1.6, okay, I'm getting nothing there. Let's just go 1.8, okay? So you see I have to go a little bit higher now. Oh, 20, that wasn't what I wanted. Okay. So you see that I have to go a little higher now because this resistor here is limiting me. Okay, let's take it up to like 4 volts. Let's see what happens there. Okay, so you can see that I can go to 4 volts and I can get something. I go to 5 volts, I can get something. I go to 6 volts. You see, I have a much greater range now. Okay, because before, if I just went up by 0.2 volts, it maxed me out. But now I've got a bigger range. I can go all the way up to 7 volts if I want. I'm still not maxed out. When I go to 8 volts, okay, now I'm maxed out. But you see I have a much greater working range now than I did before. Okay. All right, so I encourage you guys to play with that on your own, but I'm not going to require it. Any questions now about Darlington pairs and see how they allow you to get way more amplification than you could with just one transistor by itself? So give me a thumbs up, thumbs down. Yes means I understand. No means I don't. Okay, I'm seeing lots of yeses. Okay. All right. So what we're going to do now for the rest of the period is we're going to talk about that last application of transistors, the ones that up until now we haven't talked about before, and it's called a logic gate. Okay, so, all right. So if we hook up our transistors in clever ways, we can get something that is called a logic gate. And what you see here are 3 of the most common ones, but there are others. So if we look just at this one here, that is what we call a NOT gate. And the reason it's called a NOT gate is because the output is the opposite of the input. And so what we're going to do now is we're going to run our transistors in saturation mode, not in amplification mode. So what we want now is we want the resistor to either be fully on or fully off. We don't want it to be anywhere in between, either fully on or fully off. Okay, so what we're going to do is we're going to put in some voltage, and this voltage is either going to be high or low, and never anything in between. So we're going to call this a binary situation. So binary means you've got two choices. It's either on or it's off. There's no in between. Hopefully you guys know that binary is the heart of how computers work. Everything that happens inside a computer is based on a bunch of binary calculations, a bunch of binary circuits. Okay, so your input is either going to be high or it's going to be low. High is usually considered to be 5 volts, although it could be 4.5. Low is usually considered to be 0 volts, although it could be anything up to about a half volt. Okay, so what we're going to have is we're going to have a circuit here where our input is either 5 volts or 0. And this is going to be our output. And the output is also going to be 5 volts or 0. But if we hook this thing up the way that we've got it right here, this is a NOT gate. So what that means is the output is going to be whatever the input is not. So if the output is, if the input is high, the output is going to be low. On the other hand, if the input is low, then the output is going to be high. Okay, so this is called a NOT gate, and it's also sometimes called an inverter. Okay, and so your homework today, or maybe we'll do it in class, but your assignment today is to use Tinkercad to create a NOT gate. But before you do that, let's talk about the other possibilities here. Okay, the other possibility is this one right here. This is called an AND gate. And the reason it's called an AND gate is because the output will be high only if the input A and the input B are both high. Okay, if they aren't both high, then the output will be low. So let's say that the input for A is high, which means 5 volts. The input for B is low. Let me make that so high and low. Okay, so you'll see that they are not both high. Therefore, the output is going to be low. If, on the other hand, this is high and this is also high, then this will be high. Okay, and then the other possibility is, if this is low and this is low, then this is going to be low. So the only way that you can ever get a high here is if you have both a high on this input and also a high on this input. That's why it's called an AND gate. And I'm sure you guys can figure out from there how this other guy over here works. If he's called an OR gate, then I'm sure you can figure out, well, what that means is that the input or the output here is going to be high if either A or B is high. So that means you can have A be high and B is low, and that'll be good. That'll be high. Or you could have A low and B high. That would work too. That would give you a high. Okay, but if A is low and B is low, then the output here is going to be low. Okay, so you can see why they call us an OR gate, an AND gate, a NOT gate. The names do in fact make sense. Okay, now you might wonder, why do we want these? Well, next time we meet, I'm going to show you how it is that you can make an electronic circuit that adds numbers using these logic gates. So if you want to do 2 + 2 = 4, you can build an electric circuit where you input the binary number 2, you input another binary number 2 in the other one, and the output will be the binary number 4. And you can take that, any level that you want. So you are going to learn how it is. So when you come to class next time, you're going to learn how to add 2 + 2. or 2 plus 3, or 1 plus 1, or 1 plus 3, or whatever, using electronics to do it. And the heart of it is a logic gate. Okay, so the schematics that you see here are really important. Now, hopefully these are not the first time that you saw those schematics. Hopefully you read the thing that I asked you to read. Remember in the quiz that we took, I said, before you take the quiz, I want you to read this web page. Okay, so if you look on this web page, and which I know you read, right? Okay, so if you scroll down far enough, and now I admit there's a lot to read on this one. This is why I'm not surprised that maybe some of you didn't read it all. But if you scroll down right about here, okay, bingo. This is the NOT gate. Scroll down a little bit more, this is the AND gate. Scroll down a little more, this is the OR gate. Okay, so this is where we get the circuits here. So guys, I know that several of you don't always do the reading that I ask you to do. Please do it. There's tremendous things to be learned from doing the reading. Okay, so let's go back to my collection of nifty circuits that I've built. And let's take a look. So what I've done is something that I'm going to ask you guys to do. I never ask you to do things that I haven't already done myself. You can see here, I've got a couple of gates here. I've got a NOT gate, I've got an OR gate, and I've got an AND gate. So let's start with the AND gate. So let's tinker that. And so this is something that I'm going to want you guys to build eventually. If you were to do it today, that'd be great. But if you didn't want to do it today, that's okay. All right, so I'm getting my power from this battery pack here, where I've got 3 AAA batteries. Each one is 1.5 volts. So what that means then is my input voltage here on this red line is 4.5 volts. And so that's what I'm going to consider to be a high. And okay, so I've got 2 switches here. So what's going to happen is when I push this switch, then the light right here comes on just to verify that it's been pushed. But the important thing is that when let me clear this out here. So the important thing is when I push this switch, the electricity flows through here, comes through this resistor to the input of that transistor there. Okay, and then when I push this switch, it comes through here to the input of that transistor there. And if you connect things up the way that they're shown here, this light will come on only if this button and this button are pushed. Okay, so let's see if I built the circuit correctly. Let's turn on the simulation. So when I push this button on the left, you see it comes on. So you know I'm pushing the button on the left, but over on the right, we're not getting anything. So let's try this button. Okay, nothing. Now, here's an interesting question. How do I turn on both buttons at the same time? Because if I try to do it, Tinkercad won't let me. Well, there's a neat trick in Tinkercad. If you hold down the Shift key at the same time that you click the button, then you can move the mouse away and the thing stays on. Okay, so remember that. Hold down the Shift key and that locks the button down. Okay, so now when I push the button on the left, if everything works right, then my light over on the right should come on. Let's see if that happens. Yay, it works. Okay, so you'll see that what I've built here is in fact an AND gate. Okay, good. All right, oops, I didn't mean to do that. Let me go back in here again. All right, so let's stop the simulation. Let's go check out my OR gate. Let's see if the OR gate works. Okay, so here's my OR gate. So remember the idea with an OR gate is the light comes on if I push either one of the input buttons. Okay, either the one on the left or the one on the right, that should work. So I start my simulation. So when I push this one, yep, you'll see the one on the right comes on. Now I let it off, it goes off. Now I push the second one. Okay, yep, the one on the right goes on, good. So it looks like the OR gate is working fine. Now, just for grins, what would happen if I turn them both on? So I'm going to hold down the shift key and I'm going to click that. And now I'm going to click the other one. And you can see, yeah, it stays on. Okay. All right. So, yep, I think my OR gate is working the way that it should be. Okay. Now let's go back to the last one. And which, by the way, this is going to be the first one that I want you guys to make. As soon as I finish demonstrating this to you, it's going to be your job to make the circuit that I'm about to show you. So this is the NOT gate. The reason I want you to start with this one is because this one is simpler than the other two, obviously. Okay. Okay, here we go. All right. So I've only got one button this time because a NOT gate only has one input. So hopefully you guys remember the way it works is the output is whatever the input is not. So when the input is low, that means the output should be high. So that means as soon as I start this simulation, my output light should immediately come on. Let's see if that happens. Hey, yes, it works. Okay. Now, as soon as I push this button over here, my input light will come on and my output light should then go off because remember the output is whatever the input is not. So if the input is high, the output needs to be low. So let's make the input high. Hey, what do you know? It works. Okay. So when I let go, it comes on. When it comes, okay. So you see my output is whatever the input is not. Okay. So this is called an inverter. Okay. So your job is to make this circuit. Now, obviously you can just copy mine, or you could in theory just copy mine. Please don't do that. Make yours different somehow. You know, just put the things in different orders. I mean, obviously it's going to have to be very, very, very similar to mine, but don't make it be exactly the same as mine. Okay, so let's go into Canvas here. And come on. Okay, so here is the homework for tonight. Okay, so transistors in logic gates, part 1, the NOT gate. So the only thing that I am going to require you to do today is a NOT gate. Later, I am going to require you to build an OR gate and an AND gate. So if you finish the NOT gate quickly, you might as well go ahead and get started on the other two because I am going to ask you to do it eventually. But for right now, all I'm going to require you to do for tonight is just the NOT gate. Now here is a link to that same page that we talked about before. So this, if you finish up the NOT gate first, and you want to do the AND gate and the OR gate, if you click on here, you come down here and you use the schematics there, that'll show you what to do. Okay. But for the NOT gate, I've already gone ahead and copied the schematic. So here's the schematic for how a NOT gate works. And last night when I did this, I was feeling very generous, maybe too generous. I don't know. I might regret this, but I was feeling in a generous mood. So what I did here was that I actually put a photograph of my NOT gate here together with the values of the resistors that I used. Okay. Now, if you look on the web page that tells you how to do this, so let's say, let me scroll down. Hang on just a second here. Okay. So now let's annotate this. Okay, so if you look on the schematic, they tell you you need to have a resistor here and you have a resistor here, but they don't tell you what the value of that resistor needs to be. And when you guys play around with this, you're going to discover that if you make this resistor here too high or too low, same thing with this resistor, if you make it too high or too low, you're going to find that it's not going to work. So I'm just going to let you guys play with that and figure it out on your own. But if you look here, you can see the values that I used. Okay, so right here, you can see I used a 220 ohm resistor. Here was a 220 ohm resistor. Here was a 1000 ohm resistor. What I want you guys to do is play with these resistors and, you know, try different values. Find out what happens if instead of using a 1000 ohm resistor, you use a different one. Play with it. See what happens. Okay. that's a big part of what I want you guys to do today is basically just play with Tinkercad, experiment around. Okay. So the first time you do it, if you want to use the same resistor values that I did, then okay, fine. But then experiment with other things. Okay, so once you get it working, then I need you to share your circuit with me. And remember, if you just go up to the URL and type in, if you just copy and paste the URL and send that to me, it will not work because Tinkercad will not give me the permission that I need to get access to your file. The only way that that it will work is, okay, hang on a sec while let me clear this out here. Okay, so in order for you to share your creations with me, you have to go to the share button in the upper right. Sorry it takes so long here. Okay, you have to go to the share button and then you have to do the invite people option and then bingo, there it is. That's the one that I need. Okay. Are there any questions about what tonight's homework is or any questions about anything at all? Not hearing any, not seeing any. Okay, so we've still got more than 20 minutes left. Hopefully that will be enough time. So if you guys get to work right now, you can get that NOT gate built before 3:40, and then you won't have any homework tonight. Remember that at some point in the not too distant future, I am going to require you to build an AND gate and an OR gate. So might as well get started now, right? Play around with it. Have fun with this. I think most of you will find this to be fun. Some of you, I'm not sure, but most of you, I think, will be fun. Okay, so if you want to go ahead and type bye into the chat box and then head out, that'll be fine. If you wanted to ask a question, but you didn't want it recorded, here, I'll stop the recording right now so that then you can ask your question without it being recorded.